Thorium Reactors, an oral presentation by Robert Millward. The objectives of this presentation will cover an introduction to thorium reactors, types of thorium reactors, the viability of thorium reactor technology, proliferation, and safety. So what exactly is thorium? Thorium is a naturally occurring element found all over the world, but it's actually not a fissile material. It is a fertile material. And what this means is that it's not capable of fission in a thorium state. But in the process of getting energy in a reactor, the thorium is exposed to a neutron source. This thorium will absorb a neutron and become uranium-233. When an additional neutron is absorbed, it becomes capable of fission. When a neutron strikes it, it results in fission, which causes a release of the thermal energy that can be used in other thermodynamic processes. So thorium starts out as a non-fissile material, but becomes fissile through the process of the reactor operation. The types of thorium reactors. I will discuss three different types. The first one being the fast neutron reactor. There is application for thorium within the fast neutron reactor technology. However, it would not provide any real benefit to these reactor systems. Due to the operation of the fast neutron reactor, it's required to have a highly fissile material within the core, since there's no moderator in use. Perhaps one of the best types of applications for thorium would be in a molten salt reactor. The thorium is combined with the uranium to provide the neutron source, and both are liquefied into a salt form and circulated through the core. Now the core has the moderator built into it to thermalize the neutrons. Because the salt has to be kept at a high temperature between 700 degrees centigrade, it allows for a high differential temperature. And what's really great about this is that the reactor can be kept at atmospheric pressure, whereas with a water type moderator at these temperatures you have high pressures, and it requires more engineering to be involved. So you're dropping the pressure, which is making the reactor safer to operate. There's also applications where if you get into a meltdown situation, the fuel can be removed from the core into a tank. Now without the moderator, fission basically stops. So your fuel is no longer splitting atoms because it's not in the core anymore. So that's another application that makes it even safer. And then also because the fuel has changes in density with temperature, it would give the reactor a negative temperature coefficient reactivity. So this would make the reactor more easily to control. As reactor power goes up, temperature goes up, which causes density to decrease, which will cause a decline in reactor power. So these are just a few of the great applications that thorium would have within a molten salt reactor design. Another method of a thorium reactor would be an accelerator-driven reactor. Basically, you would have a particle accelerator that would accelerate alpha particles to 90% the speed of light, and then strike heavy metals such as a foil or lead. And this creates what are called spallation neutrons, and these are what will be utilized to convert the thorium into uranium-233 and then split when another neutron is absorbed. This will give you the thermal energy for your thermodynamic process. Now these spallation neutrons are required to maintain the criticality, so if you need to shut the reactor down, you would just turn off your accelerator. Now the problem with this is that accelerators require a lot of energy in order to accelerate matter to 90% of the speed of light. You're talking about gigawatts worth of energy to accelerate a few particles. So this is an engineering problem that would have to be overcome in order to use this type of reactor. But one method that has been utilized is that by maintaining the reactor very close to criticality on its own, and then you're able to use a lower power proton beam to push it just over the hump into criticality. So basically the reactor has a potential to be critical on its own, but without the proton beam it can't do it. But this is just more of a theoretical type reactor for now, as it needs further research and development to get it operational. Thorium reactor-based technology is very viable. There have been several significant demonstrations of this technology. From one example of this from 1965 to 1969, the Oak Ridge National Laboratory built and demonstrated the operation of a molten salt reactor. They used uranium-233 as the fissile driver to provide the neutrons to convert the thorium into a fissile material, and their mixture was a lithium-beryllium salt that was heated to 600-700 degrees Celsius. This reactor did operate at atmospheric pressure and was definitely a pretty safe design. And this demonstrated that thorium-based nuclear technology is possible, and that the reactor was successfully operated, generating energy. One problem that they found is that the salt mixture would actually have a lot of corrosion problems. So, this is one of the engineering problems that we'll have to figure out if we continue to develop this technology. Proliferation in nuclear technology. It's going to happen, right? So, what's so great about thorium and proliferation? Basically, it's a lot more difficult to use thorium byproducts or thorium itself to make weapons. Thorium cannot be used to make a weapon. It's not a fissile material. It requires a conversion process that can only be done in the core. So that's one of the benefits, is that you cannot steal the materials prior to it being installed within the core and converted. So that's one of the benefits of it. Now, through the thorium energy process of the core, it does generate uranium-233, which can be used to make small yield weapons. However, because of the operation of the salt, it's kept at high temperature. They would have to remove this from the core in the liquid form, so they would have to handle it as a molten liquid at 400 to 700 degrees centigrade. It may be a little bit difficult. Also, the process of using thorium in a nuclear process creates uranium-232, which is a gamma emitter, a very powerful gamma emitter. Now, you might think that this was an engineering problem, but actually it would make it more detectable if somebody had removed it from the core. It'd be very difficult to shield against the gammas. In thorium reactors, they also use up more of their fuel. That's one of the benefits of it, is you get more energy out because you're using more of the fuel itself through the nuclear process. So after the core has run its core life and the fuel is nearly all used up, there's less materials that you can use to make weapons. So proliferation in thorium, it's a great technology. It's more difficult to make these weapons of mass destruction. Some of the safety benefits with thorium reactors: improved proliferation resistance. Basically, it's more difficult to weaponize the byproducts and the thorium itself. So that improvements in proliferation. It also has potential for low pressure reactor operation, which takes less engineering to to contain the pressures. Since it'll be operating at atmospheric pressure, it decreases the dangers of a high pressure rupture in the reactor core. And also molten salt reactors, there's a possibility that you could have a freeze plug meltdown prevention. And what this is if you approach a meltdown situation, say a loss of power, a natural disaster, you can't get power to maintain the reactor operation. This freeze plug, if not maintained frozen, will melt and allow the liquid fuel to drain out of the reactor. Now the liquid fuel wouldn't have its moderator, so then the fission process would stop and the fuel would be safely stored in a meltdown tank, I guess. And there's also less nuclear waste generation, so you wouldn't have to handle nearly as much nuclear waste since more of the fuel is used up in a more efficient process. So these are just a few of the safety benefits of using a thorium-based nuclear technology.